Okay, 14.5 is the chain rule. Okay, the chain rule for 3 dimensions. Okay, recall that dy dt, oops, dy dt is equal to dy dx times dx dt. Okay, this is your chain rule. Okay, for 2 dimensions. Okay, chain rule for 2 dimensions. Okay, or we could write this as y prime of t is equal to f prime of g of t times g prime of t, right? Derivative of the outside times the derivative of the inside. Okay, well, we can parameterize this on one variable, okay? So let's say that we have, instead of this guy, we have z, right? Z, and we're going to parameterize on t. Okay, so whereas like it was g of t, f of t, okay, instead of x, just think of x as your, t as your x, and we're going to make it a parametric equation on t, okay? But then we end up with an x and a y value, okay? It's an x of t and a y of t, okay? So think of it like that way, okay? So, so we're going to use the chain rule. We're going to call this case number 1, okay? And this is where we parameterize on one variable. And we're just going to parameterize it on t. Parameterize on one variable. And we're going to call that variable t, okay? So this is when you have, okay, a function of x and y, and we're going to parameterize that function of x and y on t. You need to get it down to one variable, not 2. Okay, so this is when we have z is equal to, okay, f of, we could say x, y, but it's going to be f of g of t, comma, f of h of t, or f of g of t, comma, h of t. Okay, where x equals g of t and y equals h of t. Okay, does that make sense? So it's kind of like, hey, we have a multiple variable function, but we're going to parameterize that x and y on t. Okay, then if this is true, okay, if we have this scenario, then dz dt, the derivative of a z, or z prime, with respect to t, is equal to the partial of z with respect to x times dx dt, okay, plus the partial on y, or sorry, of z with respect to y times dy dt. Okay, so I know my d's and my partials look similar, but just make sure that you know these are partials. Okay, and the others are not. They're just straight derivatives. Okay. Okay, so that's the chain rule for case 1. Okay, let's do an example of case 1. Okay. If z equals x squared y plus 3xy to the 4th, where x equals sine 2t and y equals cosine 2t, find dz dt, okay, or we could say just z prime. Find z prime of t, okay, for t t equal to 0. Okay, so let's find the derivative when t is equal to 0. Okay, so how are we going to do this? Well, okay, the partial of z with respect to x. So let's find our partials first. Partial of z with respect to x is going to be 2xy plus 3y to the fourth. Excuse me. Okay. And then let's do dx dt as well. Let's do dx dt. What's dx dt? That's x prime. So this is x prime of t. And what is that derivative? Well, that's just 2 cosine 2t, right? Okay. Okay, what about the partial of z with respect to y? Well, this is going to be x squared plus 12xy cubed, right? Okay, and then what about dy dt? Okay, that's y prime of t, okay, which is going to be equal to negative 2 sine t, negative 2 sine 2t. Okay, negative 2 sine 2t. Okay. Okay. So now let's put this all together. Okay. So dz dt, or what we're calling z prime, is going to be equal to, okay, the partial of x, dz dx, times, okay, x prime of t, plus dz dy, or the partial of z with respect to y, times y prime of t. Okay. Okay. So this is going to be 2xy plus 3y to the fourth, right, times x prime of t. Well, what is x prime of t? We calculated that. That's 2 cosine 2t plus dz dy, that's x squared plus 12xy cubed times y prime, which is negative 2 sine 2t. Okay, nice. So far so good. Okay. So here's the deal, though. This is 2 x of t, right? This is an x of t. Okay, so we could multiply this all out if we really wanted to. We could plug in the x's and y's here, okay, and deal with it that way. However, we know that the end result is going to be that we're going to find z prime of 0. We just want z prime of 0, which is going to make some things nice here. Okay, if z prime of 0, then what is this? This x is really x of 0 when t is 0, and this y is really y of 0. Okay, so let's go to the other side here, and we're going to be like, okay, so x of t was equal to sine 2t. Okay, well, when t is 0, okay, when t is 0, then the sine of 0 is 0. Boom. Nothing's just going to go to 0. Okay, so x is 0 when t is 0. So when t is 0, implies x equals 0. And then what's y? What will y be if, what's y of t? Well, that's cosine 2t, which is the cosine of 0, which is 1. So this implies that x is equal to 0 and y is equal to 1. Okay, so I'm going to plug this in. This is going to be 2 times 0 times 1 plus 3 times 1 to the 4th, right? Okay, so I'm going to kind of run out of room. Let me go a little lower here. Okay, so z prime of 0 is equal to, well, this thing is going to go to 0, but I'll just plug it in. 2 times 0 times 1 plus 3 times 1 to the 4th times 2 times cosine of 2 times 0, right? Okay, plus, now this whole thing over here is going to go to what? It's going to go to 0, right? If I take the sine of 0, that goes to 0, which wipes everything else. So that goes to 0. Okay. Okay, so what is this going to become? Well, this goes to 0. This is going to be 3 times 2 times the cosine of 0, which is 1. So z prime of 0 is equal to 6. Good stuff. Okay, that's case 1. Okay, let's look at case 2 here. Okay, so z is equal to f of xy, but now x and y are two variable functions themselves. It's kind of like two variables with two variables. Like, oh, two variable inception here. Okay, this is when we parameterize. Parameterize on two variables. Okay, what happens if we have to parameterize on two variables? Well, this is when x equals g of s of t, or g of s and t, I should say, and y is equal to h of s and t. Okay, so two variables, but we're parameterizing on two variables. Okay, function inside a function, right? So that's the chain rule. The chain rule is like function inside a function. Okay, so this is case 2. So for this one, we can only take partials here. Okay, the partial of z with respect to s, okay, our first variable, is equal to the partial of z, okay, with respect to x, times the partial of x with respect to s, plus, okay, now there's two parts to this. There's two parts to z. Z, it has a part of x, which is of s and t, and but it also has with respect to y for s and t. So we're just going to break up the y with respect to s now. Okay, so this is now going to be dz, or partial of z, I should say. Okay, partial of z with respect to y times the partial of y with respect to s. Okay. Okay, same thing with t. Okay, so again, the partial of z with respect to x, but now we're going to take a partial of x with respect to t, the second variable. Take the partial of the partial. Okay, plus partial of z with respect to y times the partial of y with respect to t. Okay, so we have these two chain rules, okay, we can find the partials of with respect to s and the partial with respect to t. Okay, can't take the full one because there's two variables. Okay, if we only have one variable, then we can find the full derivative, but we don't have just one variable. We have two variables here, so we have to do a partial. Okay, but we're doing partials inside partials because it's a function of partials. It's a function of multiple variables. It's like here I have two vars, and then inside it, I have two vars. Okay, well, let's do one var. Okay, so we took two vars and we did one var. 2 to 1, I can find z prime. Okay, but if I do two vars inside two vars, okay, then I can only take my partial of z. And I have to find a partial of z with respect to the first variable. Okay, s, and then we need to, and we can find a partial with respect to the second variable, say t. Okay, so here we can find our derivative with respect to t for one variable. If it's 2 to 1, we can actually find the derivative. Okay, implicit derivative there. Okay, here we have to do partial derivatives. It'd be like if if I had, you know, x and f of x. You know, let's call this g, right? G of x and f of x. So it's the same thing. Okay. So here we just have we have a function of x and y. Well, what can we do there? We can take a partial of, we'll say this is z, partial of z with respect to x, and a partial of z with respect to y. Okay, so. But then if you have a function inside a function, then you get the idea. Okay. Okay, so let's do an example of this. Okay, if z equals, it's getting really hot. Okay, if z is equal to e to the x sine y, okay, where x is equal to st, equal to st squared, and y is equal to s squared t, find the partial of s and the partial of t. Find partial of z with respect to s and the partial of z with respect to t. Okay, so we use the chain rule here. Okay, so we're going to say partial of z with respect to s is going to be the partial of z with respect to x times the partial of x with respect to s plus the partial of z with respect to y times the partial of y with respect to s. Okay, so let's figure all this out. What's the partial of z with respect to x? You have a question? Okay. So partial of z with respect to x, well, that's just going to be keep x the variable and make y the constant. So what is this? This is going to be ex sine y. It's the same thing. Derivative of e to the x is e to the x. Okay. Okay, what about, let's do dz dy. Dz dy. Okay, what's dz dy going to be? Well, dz dy is going to be e the x, treat that as the constant. Okay, and then this is going to be cosine y. Okay. What about dx ds? Okay, dx ds. Okay, take s with respect to the partial derivative with respect to s, and that's going to be t squared. And then what's dy ds? Okay, well, that's going to be 2st. Okay, now let's put it all together. So the partial of z with respect to s is equal to, partial of z with respect to s is equal to dz dx, which is e to the x sine y, times, okay, dx ds, which is t squared, okay, plus dz dy, okay, okay, which was my e to the x cosine y, okay, times dy ds, which is 2st. Now, I am going to plug in, I don't want 4 variables here, I only want 2. Okay, I want dz ds in terms of s and t. Okay, I only want this in terms of s and t. So, well, I already know what x and y are in terms of s and t. That's the parameterization. Okay, so what was x? Well, this is going to be, I'm going to rewrite this as t squared first. This is going to be t squared times e to the s. What was x? X was st squared. Okay, sine of y. What was y? Y was s squared t. Okay, so we got that bad boy there. And then the next one, e to the x cosine y, same thing. I'm going to put the 2st in front. Times, this is e to the st squared times the cosine of s squared t. Oh, okay, and so that is the partial of s with respect, partial of z with respect to s. Okay. Very similar to what we did before. This would be just, we'd have to find dx dt and dy dt. So the partial of x with respect to t, okay, is going to be equal to what? So, sorry. Okay, if x is st squared, then this is going to be 2st. So it's just kind of reversed. And, sorry, with respect to t, yeah. And then dy dt, okay, partial of y with respect to t is going to be s squared. So what's dz dt? Well, dz dt is going to be dz dx, which is the same thing that we had here, times, so this is dz dx times dx dt, okay, which is this thing here. Okay, so it's kind of like they're going to reverse. So this is going to be 2st times, we already know what dz dx is. It's est squared sine s squared t plus, okay, plus dz dy of dy dt. Oops, not d. It's a Latin d, not an Arabic d, which is what we use in English. Okay, Latin d, what we call a script d. Okay, And so what is this going to be? Well, dy, dz, dy, we already know what that is, and dy, dt, I'm going to put that in front. S squared times e to the st squared, what was it, sine, cosine, s squared t. Are there some 2's there that are missing? No, I think that's good. No, I'm good. That was the last one. Okay, nice. Nicely done. I don't say so myself. Okay. Now, if you weren't confused enough, let's confuse you even more by making this general. What if I had 3 variables inside 7 variables? You'd be like, I would quit the class. You're like, oh, of course. Okay, but don't run away too soon. Okay, so general version of the chain rule. Okay, general version of the chain rule. General version, I can't spell, version of the chain rule. Suppose u is differentiable. It's a differentiable function. Okay, suppose u is a differentiable function of the n variables, x1, x2, x3, all the way to xn, and each xi is a differentiable function of the m variables, okay, T1, I don't know why they didn't use S here. I would have used S, but maybe S is reserved for something else. T1, T2, T3, Tn, or Tm, sorry. Because M and N do not have to necessarily be the same. You don't have to have a 2 by 2, or you could have 3 by 2, or 7 by 5. Okay. Then, how do we find the partial? Okay. Then, the partial of u with respect to t sub I, okay, any of these t's with respect to t, s, with respect to t, with respect to v, with respect to w, with however you want to label them out. You know, maybe this is your s, and maybe this is your t, and maybe this is your w, maybe this is your x, or not x, no x. Maybe this is your, you know, r, whatever, right? So, okay, so that's what it's saying here. We're saying du ds, du dt, du dv, or not v, du dw, du dr. Okay, how do we find any of those? Okay, because again, go back to this one, or we say I was d partial of z with respect to s. That's the first variable. Partial of z with respect to t, second variable. Partial of z with respect to blah blah blah, right? Okay. Okay, partial of u. U has a bunch of variables, and right. So this is going to be, okay, the partial of u x1, and the partial of x1 with respect to ti, okay, whichever t that you're wanting, okay, ti, plus the partial of u with respect to x2 times partial of x2 with respect to your next variable, this variable ti, the ith variable, plus du dx3, okay, dx3 times the partial of the ith variable, plus dot 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 all the way to dxn over, oh sorry, du xn times dxn over the ith variable. And then you just repeat it for whatever variable you want. Okay? However many variables you want, you got to take those partials of the upper variable times the partial with respect to that upper variable of one of the lower variables, right? So say you have x, y, z, w, right, as your upper variables, and you have, say, s, t, r, and k as your lower variables, then how are you going to find d, z, d, s? Well, you'd have to say that this is going to be d, z, dx with respect to dx, ds plus d, z, dy with respect to dy, ds plus d, z, d, I guess I can't do z, let's do u. U is a function of these. Okay, u, so this is u. I used z already, which was stupid. Okay, u, okay, I'll say, yep, and this is d, z, ds, right, blah, blah, blah. Okay, let's do plus d, u, d, dw, okay, times dw ds, right? And this is how you get ds. So it's just saying, look, and then you could get 4 of these, right? It's going to be a 4 by 4, right? 4 by 4. Okay. 4 terms and four partials. Each of them. Okay, and so you would say, oh, well, this is going to be du dt equals blah, 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 du dr equals blah, 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 and du dk equals blah, blah, blah. And that's how you do it. Okay, I'm not going to spend a whole lot of time on doing one like this. Just know that you can. And you may be asked to do one in the homework, a small one, maybe like a 2 by 3. Okay, implicit differentiation. Okay. Okay, if f of xy is equal to 0, then dy dx, the derivative of y with respect to x, is equal to negative partial of f with respect to x over the partial of f with respect to y. Okay, so that's kind of interesting. Okay, so how does this help me? Well, say I have a function of xy and I set it equal to 0. Okay, I can implicitly differentiate that, okay, using this formula. So let's do an example. Okay. Is it example 2 or 3? I think it's example 3. Okay, find y prime if x cubed plus y cubed equals 6xy. X cubed plus y cubed equals 6xy. Okay, so what do I want to do? I want to set the function, I want to create a function that's equal to 0. Right? So, oh, okay. So just toss this guy over to the other side. X cubed minus 6xy plus y cubed equals 0. Okay, and so now what do I want to do? Okay, well, I want to find my partials. I want to say, this thing is f of xy, and I want to find my partials. Okay, what's f sub x of this thing here? Well, that's 3x squared, right? 3x squared, okay, minus 6y, right? 6y. Okay. Cool. Okay, and then what is f sub y? Well, that's going to be negative 6x plus 3y squared. Okay, cool. And so if I were to implicitly differentiate this, okay, if I were to want to find the derivative of this of say y prime, right? So what's dy dx? Isn't that y prime? Y prime. If I want to find y prime, okay, well, this is just a fast way of implicitly differentiating. We already know how to implicitly differentiate. I'm not showing you anything new here. I'm just showing you, say, look, let's use the power of partials to make it faster, okay? Because this is saying that, look, y prime is now going to be equal to negative of the top, f of x, f sub x, I should say, f sub x over f sub y. Okay, so this is negative, okay, 3x squared minus 6y over negative 6x plus 3y. Okay. So if I bring the negative down and I multiply through, okay, then this becomes 3x squared minus 6y over 3y squared. Is that right? Negative 3y squared over, do I want to do that? It doesn't, I don't know. Maybe it doesn't matter. Okay, negative 3y squared. I guess it really didn't matter where I put the negative. But plus 6x, right? So let's factor out a 3 from the top and the bottom. Okay. Okay, actually, I'm going to factor out I don't know, whatever. Let's factor out a 3 on the top and bottom, and we would get x squared minus 2y over 6, or over 2x minus y squared, right? So we get something like that. Okay, and so I'm going to say that this is y prime. Boom. Like, okay, just clean that up below. Now let's check it. Let's check this. Does this work? Let's check this. How am I going to check this? Well, what's the original one that we wanted to take the implicit differentiation of? Well, I want to find y prime of this thing. Well, in Calc 1, how would we do this? Well, in Calc 1, let's just use Calc 1 to check this. Well, what's the derivative of 3x? Well, that's 3x squared. What's the derivative of 3y? That's 3y squared y prime is equal to, this is going to be a product rule, 6 derivative of the first times the second plus the derivative of the second times the first. Okay. So now I'm going to toss this guy over here and this guy over here. I'm going to go 3y squared y prime minus y prime 6x is equal to 6y minus 3x squared. Factor out a y prime. Okay, and I get 3y squared minus 6x is equal to, okay, 6y minus 3x squared divided by 3y squared minus 6x. Okay, let me get rid of that guy. And if I pull out a negative 3, I'll get the exact same thing I got on the top. I pull out negative 3 over negative 3. Okay, I'll get 2x minus y squared over x squared minus 2y, and so it does check. Okay, so we can use partials to implicitly differentiate. Okay, what if we have 3 variables instead of 2? What if we have a function of 3 variables instead of 2? Okay, let f of x, y, z equals 0. Okay, then how would we implicitly differentiate this? Well, we can only find partials now, okay, because we're limited, okay. We can't find a full derivative, but we can find partials, okay. dz dx, okay, set this equal to 0, dz dx is going to be equal to negative f sub x over f sub z. It's kind of interesting. Okay, partial of z with respect to x. Okay, what about the partial of z with respect to y? Partial of z with respect to y. Okay, just think of this as z prime, but it's really not z prime. Okay, why? Because what was y prime? Wasn't it y prime of x basically? Right, your x variable. You're taking your derivative on x with respect to x. Well, here we take, this would be like z prime of x on x, right? It would have to be, right, the partial with respect to x, well, that's going to be x over z. Okay, partial, because again, if you think of this in 2 dimensions, or in, sorry, 3 dimensions. Okay, we're moving up to the 4th dimension here. Okay, 3 dimensions is this thing, which is z, right? And we're saying let z equal 0. Okay, and we're saying what is y prime? What's y prime of x? Well, isn't y prime of x, right? What was that equal to? That was equal to negative f sub x over f sub y. Okay, so you see how y is the second variable here and x is the first variable. Well, z is the last variable. And we're saying, what's the partial with respect to z of x, which is my first variable? And then what's my partial of z with respect to y? Because again, z is going to be a function, okay, of x and y. Just like you could write f of, I'm kind of getting all effed up here. So I'm just kidding. Okay, that's a math joke. Okay, you know, just forget it. You don't want to laugh at my jokes? Fine. F of u. Okay, just f of u. Never mind. I'm getting a little too spicy. Let me tone it down. Okay. Take it from 1,000 down to about a 10. Okay. So again, if we have, say, g, right, of x, y, right, g of x, y, and we wanted to find, couldn't we rewrite this, okay, y as, right, maybe as something in terms of x, right? So maybe we say, hey, g of x, f of x. Okay, and that's all we're doing here. We're saying, hey, you know what? Y in terms of x. Could we put y in terms of x? Okay. So and we're just saying, hey, okay. So again, it's I don't want to get too lost in the sauce, but it's just an analogy. It's analogous to what we've done already, okay, in the with 2 variables, or 3 basically. Okay, we're going to now do with 4 variables here. Okay, we have x, y, z. So dz dx is these partials, and dz dy is going to be these partials, f of y over f of z. So whatever function you're dealing with, that goes on the bottom. Okay, you're trying to find your partials of. Okay, and then again, I'm going to leave that as an exercise for homework for you to do one like that, just again knowing that they're partials if you have more than 2 variables. Okay, so let's move into 14.6. Okay, directional derivatives and the gradient. The gradient, yay, we're finally at the gradient, which is good. Good stuff. Okay, the gradient is good. Okay. Directional derivative and the gradient vector. Okay, the directional derivative kind of off the paper here, whatever, doesn't matter. Okay, the directional derivative of f at x naught, y naught in the direction of a unit vector u equals a b. It's in this direction, right? In the direction of some sort of unit vector. Okay, the directional derivative, okay, is, okay, d sub u f of x naught, y naught equals the limit, okay, as h goes to 0 of f of x naught plus ah, okay, comma y naught plus bh, okay, minus f of x naught, y naught. So both x is changing and y is changing, okay, all over h, okay, all over h. Okay, this is a directional derivative, okay, in a certain direction. Okay, the directional derivative. Remember, we had our partials, okay, were in a direction of x or in a direction of y. Now this is in a direction, we have to take into account the direction of that x is changing and y is changing. So again, think of it being on the top of the mountain here. Okay, we're on the top of the mountain, right? And we said that if we walk in the x direction, okay, then we're going to go down a certain amount, right? We'll go down a certain amount in the x direction. We walk in the y direction. Okay, but now this is saying in the direction of u, okay, how is that derivative? What's the derivative in the direction of u? Okay, some sort of unit vector that could be anything. It doesn't have to be along the x or along the y. But we are going to use partials to figure that out. Okay. Okay, so this is the derivative of the trace of f of xy on the plane through x naught, y naught, 0. Okay, it's the trace of f of xy on the plane through this thing. Okay, in the direction of AB. Okay, in that direction. Okay, and can be written, or we'll say it can be expressed, as, okay, du of f of xy, the derivative of f of xy is equal to the partial evaluated for xy of a plus the partial of on y of xy of b. Okay, so this is the directional derivative. This is the derivative of f of xy in the direction of u. Okay, because remember, think of xy, f of xy as z. And what is z that has two variables? That's just a surface. This is the graph of a surface. Okay, and so we're saying, hey, we want in the direction of AB, how do we find our derivative in the direction of A? Well, just take your partial with X, take your partial with Y, and then dot product that, right? Dot product that. Oh, okay, well, that's kind of interesting. Couldn't I rewrite this as du f of xy equals the dot product of fx xy, this is a vector, fx xy, right, and fy xy, dotted with AB. Oh, okay. That's kind of cool. That's the dot product, right? So we could think of it that way as well. Okay, the dot product. And okay, this thing has a special name. Okay, this thing, this function, this vector has a special name. It's called the gradient vector. Okay, and or we say that this is an upside down triangle F, which is del. This is del. It's called del. The upside down triangle is called del. I know there's a lot of dels and deltas and just like mathematicians, very unoriginal, very unoriginal people. Okay, this is del, not delta. Delta is upside down. This is del with no ta. Okay, so del F is equal to f sub x, f sub y, okay, that, okay, or we could rewrite it as f sub xi plus f sub yj. Okay, that's del. And we'll come back to this a little bit later, okay, but just know that you can write it like this, okay, so that's called the gradient vector. The gradient vector. Okay. Gradient vector del. Okay, let's do a couple examples. Okay, example number 1. Okay, find the directional derivative, okay, the derivative in the direction of some value, okay, the directional derivative du of f of xy if f of xy equals, okay, x cubed minus 3xy plus 4y squared. Okay, cool. Okay, but yeah, we need like a, b, something, I don't know. Okay, so let's figure out what a and b are. Okay, in and u. Here's u. It's gonna tell me what u is. And u is the unit vector. Okay. given by the angle theta equals pi over 6. What? Vector given by the angle theta equals pi over 6. Okay, then find the directional derivative of f at 1, 2, at the point 1, 2. Okay. 1, 2. I mean, it would be 1, 2, and then whatever z is. You could be in 3 space. Okay. Well, that unit vector, that's using theta. Unit vector, so what does that mean? It means I'm going to have to parametrize my unit vector in terms of theta. I want a vector of length 1 in terms of theta. How would I get a vector of length 1 in terms of theta? Well, what's a way to parametrize this so that I get radius 1? What is that called? Isn't that the unit circle? Oh yeah, that's the unit circle. Unit circle. Okay, would be cosine of theta sine theta. Ah, okay, that's kind of cool. This vector space would give me the unit circle, right? Parametrizing on theta. Ooh, okay. That's nice. That's nice. Okay. So it's good, good, good. Okay, I like what I've done there. Okay. So it's the unit vector. Okay, so what's the unit vector? What's the unit vector at theta equals pi over 6? Isn't that cosine pi over 6 sine pi over 6? Isn't that unit vector? Okay, because again, if you think about the unit circle, we're out here at pi over 6, which is 30 degrees. Wouldn't that be a unit of 1? Right, if I'm out here at, say, radical 3 over 2 comma 1/2, right? So what this really is radical 3 over 2 comma 1/2, right? Well, that's kind of cool. Okay. So let's find the directional derivative. Why am I not writing? Did it overheat? Did it freeze on me again? It's not hot. It's freezing on me. Just doing the freezy freeze. Stop with the freeziness. Okay, I guess it's that part of the. It is that part of the lecture where you guys go get a drink of water, and I reboot my computer. It froze again. This is what we call a water checkpoint. Okay, so I'm going to reboot, and I'll be right back. So go grab yourself. I mean, I grabbed myself ice cream earlier because it's hot. It's hot today. Made myself a milkshake. You know, just a little milk, a little ice cream, and then stir it up. Whip until frothy. Okay, and then you drink it. It's right here. There's not much left. Like nothing left. So, pinkies up. Make sure you have your pinkies up. It's good. It's chocolate chip cookie dough. Very tasty. Not good for my waist, but good for my mental health. So, everything is a trade-off, I suppose. Okay. Let's get back to business here. Back to business. I'm done with my business. come on, behave. Okay, we're back. Hopefully it's working again. Yes. Okay, perfect. Let's pray we can go another hour without any mess ups. Okay. I don't think we'll be going another hour. Another 45 minutes at the max. Okay. So now I can write again. That's good. Okay, so this is our U, right? That's our U. Our U. Okay, so this is our U, our unit vector. U. Okay, so what is what's f sub x going to be in this case? Bring this down. Okay, f sub x is going to be 3x squared minus 3y. Okay. What's f sub y? F sub y is going to be negative 3x plus 8y. Is that right? Okay, and so what is, okay, what's my derivative? Du of f of xy, that's going to be equal to my gradient, which is 3x squared minus 3y, comma, negative 3x plus 8y, dotted with radical 3 over 2 and 1/2. Okay, so let's dot this. Okay, so this is going to be, I'm just going to kind of distribute this over this guy and distribute this over this guy. So this is going to be 3 radical 3 over 2 x squared minus 3 radical 3 over 2 y. Okay, and then this is going to be minus, it's actually plus, but it's whatever. Okay, so we're dotting this, right? Dot producting this, so plus negative 3 radical 3 over 2, oh sorry, this is 1/2, my bad. This is negative 3 over 2 x, okay, plus 4y. Okay, and what I could do if I want, this is a function of x and y, I could try to simplify this by grouping the x's together and grouping the y's together. But, so let's see what we got here. 3 radical 3 over 2x squared minus 3 over 2x. Okay, I'm just going to factor. I'm just going to go, hey, this is plus 4 minus 3 radical 3 over 2 times y. Okay, and I kind of leave it like that. Okay, so that's my derivative. Okay, directional derivative. Okay, I could leave it here. Okay, but now they're saying we want to evaluate this for a value. What's the value? 1, 2. Okay, so we want the directional derivative in the direction of pi over 6. So it's in the direction of pi over 6 at the point 1, 2, and then whatever z is going to be here. I don't even know if I want to calculate that, but let's see what it is. 1, 2, that's 1 minus 6 plus 4? No, plus 8. 1 minus 6 plus 8, that's 3, I think. I think this is 1, 2, 3. Okay, at point 1 through 2, 3. So we have some sort of surface. I don't know what it is. Okay, but at 1, 2, 3, okay, we want the derivative in the pi over 6 direction. Okay, so we want the derivative in the pi over 6 direction. Okay, so what's the derivative in the pi over 6 direction at 1, 2, 3? Okay, of this surface, this z function. Well, du of f of 1, 2 is equal to 3 radical 3 over 2 times 1 squared minus 3 over 2 times 1 plus 4 minus 3 radical 3 over 2 times 2, right? So let's see if we can simplify this at all. Okay, this is 3 radical 3 over 2 minus 3 over 2 plus 8 minus 3 radical 3. Okay. So this is 3 radical 3 over 2 minus 3 radical 3. That's going to be negative 3 radical 3 over 2. And this is 8 minus 3 halves, which is 13 halves. And so this becomes 13 minus 3 radical 3 over 2. There we go. Nice. Okay, so what does this represent? Okay, so this represents the rate of change of z in the direction of u. This is the slope of the tangent line to the curve of the intersection of z equals x cubed minus 3xy plus 4y squared and the vertical plane, okay, and the vertical plane, okay, so it's where they intersect. Go away, dude. Okay, and the vertical plane through, okay, the vertical plane through 1, 2, 0, 0. Okay, in the direction of pi over 6. So it's saying, look, we have a vertical plane here. So again, we have this surface z, okay, and we're going out x and y. Okay, so let's say we go out 1 here, put 1 in the x, 2 in the y, place us here, right? And so we have a vertical plane, okay, vertical plane through 1, 2, 0. Okay, so through 1, 2, 0, vertical plane. Okay, so that's just that axis through 1, 2. That's just the the xy axis, xy plane. So it's saying that it's a vertical plane through this thing, and the intersection of this, okay, in the direction of pi over 6. You're saying let z equal 0. Okay, why? Where are we letting z equal 0? Oh, because it's saying this is the derivative of the trace of f of xy on the plane through on the plane through the vertical plane. Why is that saying it's a vertical plane when it should be a horizontal plane? Let me look at the book real quick. I'm getting the definition correct. The XY plane is a horizontal plane, not a vertical plane. If we let Z be 0, then the only plane that can go through Z equals 0 is a horizontal plane. So either hopefully my notes are wrong, and it should be a horizontal plane. Otherwise, we got to rethink what we're doing here. 13, 14. No, it's a vertical plane. So how the hell does that work out? A vertical plane. Oh, through that point. Oh, it is a vertical plane. It is not this plane. It is the vertical plane through this. Oh, in that direction. Ah, I get it now. Ha ha ha. Okay, so it's the vertical plane through this point in the direction of pi over 6. Okay, so in the direction of pi over 6. So it's this vertical plane. Okay, it's this vertical plane here. Oh. And where the plane and the curve intersect, that's where we're taking our derivative. That's kind of interesting. That's cool. Yeah, that makes sense because you're at 1, 2. You're at 1, 2. It's the plane through this, but the plane also goes through 1, 2, 3. So it also goes through 1, 2, 3. Okay, so it's a vertical plane. Okay, because Z can be anything in that plane, but they're just saying, I don't know why they didn't say, 1, 2, f of 0. I guess they're just letting Z0 make it easy to draw the plane of intersection, but yeah, so that makes sense. Okay, good. Yeah, picture is worth 1,000 words. Okay. So yeah, let Z equal 0. That and that. Okay, because it's a plane in the Z direction, can be anything. Okay, but it's that specific angle that we're looking for. Okay, pi over 6. Okay, let's do another example. Example 2 here. Okay, find the directional derivative of the function x squared y cubed minus 4y at the point 2, -1. Okay, in the direction of the vector v equals 2i plus 5j. Okay, so again, we're going to say that the directional derivative is equal to del f dotted with AB. Okay, del f dotted with AB. Okay, or u, we could basically call it u as well, dotted with u. Okay, so what's del f? Well, del f, okay, or what we call the gradient vector is the gradient. Okay, the gradient vector is the partial of x, partial of y, okay, as a vector. Okay, so what's the partial of x here? Partial of x is going to be 2x y cubed, 2x y cubed. Okay, partial of y is going to be 3x squared y squared minus 4. Okay, and then we're going to want to find in the direction of v. Well, v is not a unit vector. This is not a unit vector. This is not u. Okay, but we want to turn it into a unit vector. In order to find the directional derivative, we have to have a unit vector, u. Okay, so what's u going to be? Well, u is going to be v over the magnitude of v. Okay, so I'm going to change it into a unit vector. So this is 2i plus 5j over 2 squared plus 5 squared square root. So this is 2i plus 5j over the square root of 29. So this is 2 radical 29i plus 5 over radical 29j. Okay. If you want to write that in component form, this is 2 radical 29, 5 over radical 29. Okay. Nice, nice, nice. Like what I've done there. Okay, so we want the directional derivative at this point though. So I don't really, I'm gonna just find out, well, what's del of f at 2, 1. Okay, just plug it in. Or 2, -1, sorry. Plug in 2, -1 here. So what's that? What's that vector? That vector is going to be 2 times 2 times -1 cubed. Okay, comma, 3 times 2 squared times -1 squared minus 4. Okay, so that's 2 times 2, this is -4, comma. This is going to be 3 times 4, which is 12, minus 4, which is 8. So that's that guy. And so we want the directional derivative of f at 2, -1 is going to be -4, 8 dotted with 2 over radical 29. Oops. 5 over radical 29. Okay. So now let's just dot these. So this is -8 radical 29 plus 40 radical 29, which is 32 radical 29. That's the value of my derivative in that direction. Flip the page. Okay, again, if we had more than one variable, we could generalize this. Come on, go back. Be nice to me. Okay, so let's generalize this. Like so. Okay. For f of x, y, z, and u of a, b, c. So now say that we have 3 variables instead of 4. Okay. This is a 4th dimensional function. And u is a 3-dimensional unit vector. Okay, then del, then du of f of x, y, z would equal f sub x of x, y, z, okay, times a plus f of y, x, y, z, b plus f of z, x, y, z, c. Okay, and we would say that del f would be f sub x, f sub y, f sub z. Okay, or we could say f sub x I plus f sub y j plus f sub z k. Okay. Okay, let's see if we want to generalize that to more variables. Okay, maximizing the directional derivative. Maximizing the directional derivative. Okay, maximizing the directional derivative. Okay.
Professor, can you slow down a little bit so I can see the last line that you wrote? Thank you.
Was that Erica or Ashley?
Ashley.
So why did you take me again, Ashley?
Truthfully, because I like the way you teach.
Oh, okay.
Yes. So I was waiting to take this class. Because the last class I checked, but you didn't teach it online.
Right. Okay, sounds good. Did you pass my class before?
No. I think I may have passed the very first one I took, but that was it.
Okay, sounds good. Hey, 2 or 3 times is a charm. So this is tough stuff. So, man, it's really tough. I don't mean to call you out like that. I'm just curious.
No, you're fine.
Okay. At least I think I'm fair. But I don't think I'm like the hardest, and I don't think I'm the easiest, but I at least try to be fair. I think that's why a lot of students come back to me as well. At least that's the some of the feedback that I've gotten in the past. So, but I'm glad you like my style of teaching. Okay, so maximizing the directional derivative. Okay, for a given point of f which directional derivative okay, for a given point of f, which directional derivative produces the maximum rate of change. Okay, which one produces the maximum rate of change? That's what we want to find. We want to find the maximum rate of change here. Okay, so again, the one that goes off the cliff is probably the maximum rate of change. Okay, now, not all functions go off a cliff edge, though. Okay, remember we want to say like, you know, which directional derivative, right? So if we take a derivative in a certain direction, right? So let's say that we have a surface, and then we have a point out here. Okay, this direction may not be as much of a change as maybe this direction. Okay, that might produce more a faster rate of change. So we want to find out, well, where is this going to create a faster rate at a certain point? We call that P naught. Okay, so here's the theorem. Okay, so here's the theorem. Suppose f is a directional function of 2 to 3 variables. Okay, the maximum value of the directional derivative okay, the u f of x is, okay, the magnitude of del f of x, and it occurs there's supposed to be 2 c's there. And it occurs when u is in the same direction as the gradient vector, is the same direction as the gradient vector. Del f of x. Okay, let's do a proof of this. It's a pretty easy proof. Okay, what is the directional derivative of f? Well, that's del f dotted with u. Okay, and from the dot product, how can we rewrite the dot product in terms of theta? Well, it's the magnitude of the first one times the magnitude of the second vector times the cosine of theta, right? The angle between the vectors. Okay, and where cosine is theta is maximum at when theta equals 0, okay, and therefore cosine, and therefore cosine of 0 is equal to 1. Okay, so the max happens when the angle between them is 0. Okay. So the max of the directional derivative here is equal to the magnitude of f times the magnitude of u. Okay. But, here's the big but the magnitude of u is equal to what? What's the magnitude of u? Anybody know? What's the magnitude of u?
1,
Why?
because it always equals.
What does u stand for?
Really?
No. What does u stand for? Why are we using the letter u here? We go back to the definition. What does u stand for? U equals AB, right? AB, and why do we use u? Why the letter u?
Because it's a unit vector.
Exactly, thank you, Angie. Because it's a unit vector. Does that make sense? So U is a unit vector. What's the magnitude of a unit vector?
1.
There you go, 1. So this is by definition of unit vector. Okay, U is a unit vector. The magnitude is 1. Okay. So du of f, okay, the directional derivative of f is equal to the magnitude of the gradient. Okay. When du of f is maximum, is a max. Is a maximum. Oh, okay. Well, that's kind of cool. Okay, and occurs in the direction of what? Of the gradient function. Okay, so in the direction of the gradient function, because there's only one direction here. Okay, this magnitude, if I take the gradient function, right? Well, isn't the magnitude of the gradient function going to be in the direction of the gradient function? Yeah, so there you go. Okay, so it's in the direction of that, especially since U and F were parallel, right? They were basically in the same direction. We could say that the unit vector U is here, whereas del F is here. Well, if they're in the same direction, that means that the angle between them is 0, which means that the directional derivative is going to be in the direction of U by definition. But what also is in the direction of U? Del F. Del F is in the direction of U as well because they're on the same trajectory. They're on the same path. So, of course. So proven. Boom. Okay. 4 or 3. I think this is 3. I don't know. I lost track. Okay. If f of xy is equal to x e to the y, find the maximum rate of change and direction of that rate at 0.20. Okay, 2,0. Okay, so we want the maximum rate of change. Well, okay, so the maximum rate of change and the direction of the rate of change. Okay, so let's find out what's del F here. Del F is going to be f sub x, f sub y. Okay, that's the derivative there. Okay, so f sub x, f sub y is going to be, okay, f sub x is going to be ey, and f sub y is going to be xey. So, okay. So duf is equal to the magnitude of this thing, of del f, which is going to be equal to, okay, the square root of ey ey squared plus x ey squared is equal to e2y plus x squared e2y, okay, square root, which is equal to x, oops, e2y times 1 plus x squared, which is equal to ey times the square root of 1 plus x squared. Okay. And we want to evaluate this at the point 2, 0, right? So we want to evaluate this. So this is duf. So this is the max derivative. I'll put max here. The maximum derivative is this thing. Okay, and we want to know what's the max directional derivative of f of 2, 0, right? F of 2, 0. So this is e to the 0 times the square root of 1 plus 2 squared, which is radical 5. So radical 5 is the maximum rate of change. Okay, it's the maximum rate of change here. Okay, in the direction. So the maximum rate of change in the direction of what? Well, in what direction? Well, it's in the direction of del f. Well, what was del f at 2, 0? Well, del f, let's figure out what del f was. Del f was ey comma x ey, right? So if I plug in 2, 0 here, I get 1, 2. Okay, so del f evaluated at 2, 0 equals 1, 2. So it's in the direction of 1, 2. Maximum rate of change in the direction of 1, 2, direction of change of f in the direction of 1, 2 is radical 5. Boom. Nice. Okay. Tangent planes to level surfaces. Let's look at that one real quick. Tangent planes to level surfaces. Okay. Okay, the tangent plane to the level surface f of x, y, z equals k. Okay. F of x, y, z equals k. If you want an extra variable there, you could say, hey, it's w. You can make this w if you want. If you need the extra variable, just say, hey, it's w equals k. But these are level surfaces. Okay, it's really hard to visualize the fourth dimension, but whatever. Okay, at p of x naught, y naught, z naught. Okay, is the plane that passes through P is normal to del f, okay, the gradient, and it has equation not again. Oh, I was going to say not again. Okay, and has equation. I thought my system froze there for a second. F sub x naught, y naught, z naught, x minus x naught, plus f sub y, x naught, y naught, z naught, y minus y naught, plus f sub z of x naught, y naught, z naught, and z minus z naught is equal to 0. Okay, that is, okay, okay, that is del f, right, because this is del f dotted with x minus x naught, y minus y naught, z minus z naught. Okay, x minus x naught, y minus y naught, and z minus z naught. Okay, so let me draw a little picture of this for us. Okay, we want a tangent plane. Okay, so we have a point here. And we'll say that the surface, okay, this is the surface. The surface and the tangent plane, maybe I'll use a different color. Darken the surface in. Okay, so kind of get the idea here. Okay. So, and then we have the tangent plane tangent to this thing. Okay, at this point, tangent at this point, right? Okay, and we're saying that it's normal. The tangent plane is normal to del f. Oh, okay. So this is del f. That's the normal to the tangent plane. Okay. And so, well, what's the tangent? What's the tangent here? It's normal to this thing. Well, we're not going to go down that road. Okay, just yet. But just keep in mind that there. Yeah, I'm not gonna go down the road yet. We're not there yet. So I'm not gonna confuse you by mixing messages. But it's normal to this, to del f, right? To del f. Okay. Yeah, we just need to know that it's normal to del f. Okay, that's the tangent plane. Okay. So yeah, at that point on the thing. Okay, so yeah, is equal to 0. Okay, so we want to let's do an example here. This will be our last example for the day. Okay, is this number 4? I kind of lost count somewhere along the way. Yeah, number 3, number 4, maybe. Who knows? Okay, so find the equation. Okay, of the tangent plane and normal line at the point -2, 1, -3 to the ellipsoid x squared over 4 plus y squared plus z squared over 9 equals 2. Okay, so f sub x equals 1/2 x, right? Does that make sense? That f sub x would be 1/2 x. Okay, what's the derivative here? Okay, the partial derivative of x, that's 2x over 4, so 1/2 x. What's the partial derivative of y? Well, that's 2y. What's the partial derivative of z? Well, it's going to be 2/9 z. Okay. Okay, so we know that this is going to be del f dotted with x minus x naught, y minus y naught, z minus z naught, right? Z minus z naught. Okay, so let's plug this all in. Okay, so this is going to be 1/2 x, comma 2y, comma 2/9 z, dotted with these guys here. Okay, dotted with, I'll just put some quotes here. Okay, is going to give me my normal line. Okay, so, well, what is x, y, and z? What's x, y, and z? X is -2, so 1/2 times -2. This is 1, and this is 2/9 times -3. Okay, dotted with this again. Okay, a couple more quotes. Okay, and we're going to set that equal to 0. Okay, so this is -1. This is going to be 2, and this is going to be 2/3, right? -2/3. Okay, so this is going to be, okay, dotted with x minus x naught. Well, what was x naught? X naught was -2. Okay, and then what's y naught? Y minus y naught. Y naught is 1. And what's z naught? Z minus -3, right? Okay. So this is x plus 2, y minus 1, z plus 3, -1, 2, -2/3. Okay, so now let's just dot product this. This is going to be -x minus 2 plus 2y minus 2 plus -2/3 z minus 2. Okay, equals 0. I don't really need the parentheses, but since everything's addition. But this becomes -x, okay, plus 2y minus 2/3 z. Okay, this is -2, -2. That's easy. That's -6 is equal to 0. So what's the equation of my tangent plane? -x plus 2y minus 2/3 z equals 6. You can leave it like that if you really wanted to. If you want to get rid of the fraction, you could. You could multiply everything through by 3. It really doesn't matter at this point, but you could say, or let's multiply everything through by -3. 3x minus 6y, okay, plus 2z equals -18. Look at that. It's a nice equation of a tangent plane. This is the tangent plane. Okay. Okay, now it says find the equation of the tangent plane and normal line. Okay. Well, the normal line at the point. The normal line at the point. Okay, well, the normal line is going to be, okay, x minus x naught at plus at, right? Y equals y naught plus bt, and z equals z naught plus ct. Okay. So we want the normal line at this point, right? So we're going to say that, say whatever our surface is, and we want the normal line at the point. So we could have a tangent line through this, which we would call, okay, tangential, and then we can have the normal. But we know that that del f is the normal vector to this tangent plane, right? This normal, right? So that's del f. So del f is the normal vector. Well, v equals abc, okay, is the normal vector. Okay. Is that right? No, it's not right. No, it's not. It's not normal. Or it is the normal vector. No, you're right. It is the normal vector. It's not the normal. It's not normal to the line. It's just in the direction of the line. But what are we saying is the direction of the line? The direction of the line is del f. Del f is the direction of the line. It's normal to the plane. Del f is that direction. So if we could find out what del f is, then that gives us our vector through a point, right? Vector through a point and a vector, we can get a line. Okay, point and a vector in the direction of the line, we get the line. So del f at what? At 2, what's the point? The point is -2, 1, and -3, right? -2, 1, and -3. Okay, so the partial with respect to -2. Okay, so what was the partial here? Okay, what was del f? Del f was 1/2 x. Okay. I'm just going to scrunch it. Del f, stop, go away. Okay, del f was 1/2 times x, -2. And then 2 times 1, and then 2/9 times -3. Okay, del f. We already have that. It's right here. Okay, so I'm not going to do it again. Okay, so this is -1, 2, and -2/3. Okay, that's good. So that's going to be my ABC. Okay, so what's x naught? Well, x naught is -2. X equals -2 plus -1t. Y equals, okay, y equals y naught, which is my point, 1. Okay, plus bt. B is, again, this is a, b, c, and this is x naught, y naught, z naught. Okay, 1 plus b is 2t. Okay, and then z is equal to -3 plus -2/3 t. Okay. So let me clean this up. X is equal to -2 minus t. Y is equal to 1 plus 2t. And z is equal to -3 minus 3. Okay. This is the normal line. Okay, so we find the tangent plane, and then we can find that normal line. Okay. Okay, I'll see you guys later. See you Monday or Wednesday. I'm gonna post the study guide for the next exam. October 7th is the next exam. I have to take that day off, so you'll be taking the exam without me. Hopefully everything will go fine though, just like last time. Okay, and so yeah.
Bye. Thank you.
Okay.
Thank you, Professor.